officially introduce a normal distribution and learn how to convert X values into Z values when we have confidential data. The normal distribution, as we saw before, has a bell-shaped graph, bell-shaped graph. And remember that the graph is symmetric with respect to the mean. And remember that, well, there are always gaps in the graph and the horizontal axis, horizontal line, which represents X values. So X values are continuous variables. Like what? Like shoe sizes. Like IQ scores. Stock markets. Stocks. Like heights, like weights, and many things we can think about. Heights, weights, and many more examples. They follow a normal distribution. So you remember that we said that the graph has area below it. The area below the graph is 100% or 1. Its area is 1 or 100%. Remember that 100% is 100 divided by 100, which is 1. So when you're talking about 1, you're talking about 100%. And this gives us the probability. This area is equivalent to the probability. So when you're talking about the area, you're talking about the probability. Okay, so again, remember that we are using the actual value like X. Very well. So there's a question. Suppose you're working for government and you're a statistician. The government gives you the real data. Well, those data are mainly confidential data. You want to use the result of the data in a research. You want to present them to your classmates. Is there any way we can convert those confidential data into some data that are non-confidential, and you can use the results of the data, the analysis of the data to your classmates? Very well. So one way is to take X value and convert X value into Z score. So we are allowed to take X values, wow, confidential values, and convert them into something new that we call Z value. And convert them into Z value. Okay. Here we're going to use a nice formula to use it as a machine and convert X values into some new data like we call Z. The formula that you're going to use is this machine. You're going to take each X value, find the difference between X and the mean, X minus the mean, and then divide it by the standard deviation. Well, okay. I take each x value. I do the subtraction on the numerator. I use the mean. On the denominator, I'm going to use the standard deviation. This is a standard. This is just a normal distribution. We're going to convert the normal distribution into standard normal distribution. So let me use a different color. I'll write it on the board for you. This is our normal distribution. Normal distribution. For x values, we take x values and we convert them all into z values, and we have a new name, standard normal distribution. Very well. Okay. So what are the properties of this new distribution? It happens that this new distribution, which we call standard normal distribution, has the exact same shape. Okay. So far so good. It has the exact same shape. It is a bell-shaped graph. What about the area? The area is going to be 100% or 1. So far so good, right? The area, which is 100% or 1. Well, then what happens to x? X converts into z. Guys, when you're using standard normal distribution, your horizontal line is denoted by z values. Okay, well, x is converted into z. What happens to the mean? What happens to the standard deviation? Let us go back to empirical rule. So, from empirical rule, we can divide up a normal distribution this way. Rule says that if you have a normal distribution, whatever the mean is, 68% of the data are within one standard deviation of the mean. 68% of the data are in one standard deviation of the mean. Okay, so it means that if I have the mean mu minus one standard deviation, mu plus one standard deviation has 68% of the data. Okay, not that hard, just an approximation. Mu minus sigma and mu plus so you see that, hey, 95% of the data are within two standard deviations. 95% of the data are in two standard deviation of the mean. Okay. So let's just go further here. 95% of the data, mu plus the standard deviation, and mu minus the standard deviation. So it's going to be 95%. finally, 99.7% of the data are within 3 standard deviations of the mean. 99.7% of the data are in 3 standard deviations of the mean. These are just approximation using the empirical. Okay. Why we are writing this down? Because we want to convert each of these numbers into z-scores, z-values. Mu plus 3 standard deviation and mu minus 3 standard deviation. Okay. This is from empirical rule saying that, hey, the probability that x is within mu minus sigma and mu plus sigma is 68%, then the probability that the x value is within mu minus 2 standard deviation, mu plus 2 standard deviation is 95%, and finally, the probability or the area below the graph is 99.7%. The data, the values that we have are within 3 standard deviations of, okay. So, what are we going to do? We're going to convert each of these into z values using the formula. Remember that. Z is equal to x minus the mean divided by the standard deviation. This is a machine. You're going to take x values and plug them into this machine. This machine converts x values into z values. Let's see. Let's start by taking the mean. So my x value is equal to the mean. All right. My x is equal to the mean. This is my very first x value. I'm going to plug that into the z. So z becomes x is equal to the mean, so it becomes mu minus mu divided by standard deviation. We get 0 divided by 1 standard deviation, which is 0. So your mean is, I took the mean and I just plugged that into this machine and it gave me 0 back. Okay. So when it comes to standard normal distribution, the mean is always 0. Mean always. Okay, very good. So the next number that I'm going to use, the next x value that I'm going to use is mu plus sigma. Okay. This is for x equals to the mean. Z is 0. Now that if x is equal to mu plus 1 standard deviation, if I plug this x into this machine, what happens to my z value? What is the value of z? Z is x is mu plus sigma, minus mu, okay, divided by sigma. Mu and minus mu, they cancel out. You get sigma divided by sigma equals to 1. So this number, mu plus sigma, is nothing but z equals to 1. So your z is 1. Okay. So as you can see, you are not working with the confidential data anymore. All of these numbers are converted into 0, 1. Later on, you're going to see -1, 2, -2, 3, -3, and so on. Let's plug in one more number. I'm going to take this x value, mu minus sigma, and I want to calculate the z. So x is mu minus sigma. Z becomes mu minus sigma is my x. I'm going to plug that into this formula, into this machine. Minus the mean divided by sigma. As on the formula, I have to write it down. Mu and minus mu, they cancel out. I left with negative sigma divided by sigma, which is -1. Guys, this number, mu minus sigma, is just -1. You can convert the rest of them into z value. You get 2, 3, -2, -3, and these sides are your 0. So the mean is always 0 with standard deviation equals to 1. This is for a standard normal distribution. Again, why we did that? We have confidential data. We have information that we are not allowed to share, but you can take these X values, use this machine, Z, and convert them into some numerical values that help you to analyze the data and use it in public without being worried about the actual data being exposed.
Thank you, Kelly. So as you can see here, you have a survey. You're a statistician, you ran a survey, and you found that, hey, on average, it takes 1.5 years for people to buy a new cell phone. All right, the standard deviation is 0.25 year, and then your job, your goal is to find the probability that the user will keep the phone for less than 1 year before buying a new one. Okay. We have some indication that this distribution is a normal distribution because it says the lengths of time people keep their phones are normally distributed. Okay, so how do we find the probability? Let's take a look at our board. Let's look at our calculator here. So as I mentioned before, it doesn't matter if you use your X or your Z, but for the sake of confidentiality of your data. So X, Z. I need to write them side by side so you see what's going on. Then you have X, then you have Z. So remember that here it says find the probability that X is less than 1. Remember that we calculated Z to be -2 or equivalent. We want to know what's the probability that Z is less than -2. The same calculation for X for Z. In this case, we're going to go to second vars, find the normal, CDF, the lower limit as usual, the upper limit as usual, mean, and the standard deviation. Okay, since it's less than, and as you remember, the graph says, hey, it is less than. When you have a graph with less than, it means that you're looking at the less than area here. So it's less than a value, either X or Z. This is your upper limit, and this guy is your lower limit. Okay, in this case, here we have less than 1. So our upper limit is 1, and our lower limit is going to be a very small number, like -10. The mean, remember from the question, the mean was 1.5, am I right? So 1.5, and the standard deviation is 0.25. And now we want to use our calculator. Okay, show me how to use my calculator. Turn on your calculator. Second bars, normal CDF, cumulative density function, enter. If it's already written, this form, do not change it. Or if you feel comfortable using a negative number, remember that the negative sign is here in front of the number. This is subtraction. So the functionality that you're going to use for a negative number is this, -10, -100, a small number. And the upper limit, as we mentioned, is 1. Mean of the data is 1.5, and the standard deviation is 0.25. So let us do that, see what is the probability. Okay, guys, the probability is 0.0228, if you want to round it this way, or you can just say that is 2.28%. So this probability is approximately 2.28%. Again, using X, calculating the probability. If the data is not confidential, use the normal CDF, your lower limit and upper limit, mean of the actual data, standard deviation of the actual data, non-confidential. But if it is confidential, we converted that X equals to 1, converted that into Z, which is -2. Now, for confidential data, if we do the process, it is second bars, normal CDF, very good. The lower limit, upper limit. If you're using TI84, you're just going to use parentheses, lower limit, comma, upper limit. Just enter the numbers with comma separated, the mean, comma, standard deviation, close the parenthesis, and do the calculation. It's going to be the same. Upper limit, mean, standard deviation. We just showed that the mean and standard deviation for a standard normal distribution is 0 and 1. The lower limit, the upper limit is -2. The lower limit, just use a very small number, which is smaller than -2. It's going to be, for example, -10, -100. So second Mars, normal CDF, the lower limit, let's leave it as -10. The upper limit is -2. The mean is 0, standard deviation is 1. Now let's do the calculation. Very good. As you can see, we got the same probability, 0.0228. So the probability is about 2.28%. As you can see, the area, this small area is about, if you just move this a little bit here, it's going to be roughly around here, which is 2.28%. So the probability that cell phone users will keep their phone for less than 1 year before buying a new one is about 2.28%. Now, suppose we are interested in knowing what is the probability that they keep their phone for more than 2 years. So far, we calculated that for less than 1 year. Just showed you how to use that. Now I want to know what is the probability that they keep their phone for more than. The keyword is more than. And I say, hey, the data are not confidential, are confidential. You are allowed to use them. It means that you are allowed to use X values. They are non-confidential. So let's take a look at this. More than 2 years. What is the probability that X is more than 2 years. So it says more than, what's the graph like? When we are talking about the graph of larger than, it means that it is on the right-hand side of your X value. This is just a general graph. This is just a general graph. I want to know, what is this probability? What is this area? This area is your probability area. What is this area? What is the probability? And it is larger than. So take a look at this. It means that my lower limit is going to be here, and my upper limit is far on the right-hand side. So take a look at this. My lower limit, and this guy is my upper limit. Where is that? I don't know. The graph keeps going. Remember that the graph never touches this horizontal axis. It just keeps going. It's going to be very small, but it keeps going. All right, very good. So second, VARS, normal CDF, lower limit, upper limit, mean, and the standard deviation. Okay, so what is my lower limit here? Remember that it says larger than 2, like 3, like 4, like 5, so my lower limit is 2. What about my upper limit? Use a large number, positive large number like 10. So lower limit is 2, upper limit on the right-hand side of 2, you get positive numbers, mean the same as the mean of the data, and standard deviation the same as the standard deviation of the data that we have. So let's take a look at a calculator. So let's turn on the calculator. Second VARS, go to normal CDF, lower limit is 2, upper limit is positive 10, and mean is 1.5, and standard deviation is 0.25. Now let's do the calculation. And as you can see, it is 2.28%. So 2.28%. The probability that users keep their phone more than 2 years is also small, 2.28%. Very good. Another question. What is the probability that they keep their phone between 1 to 2 years? What is this probability? How do we calculate the probability in between 2 numbers? Thank you, Juliet. Very good. So what do we have here? Thank you, Beth. It says in between. Hey, now my graph has its lower limit and also its upper limit. Both of them are mentioned in the question. I have both of them. So in general form, in between is going to be the area in between 2 numbers. So the lower limit is going to be the smaller number and the upper limit is going to be the larger number. So this is my lower limit, and I have my upper limit. Very good. So let's use our calculator. This is what we're doing. We're going to second, we're going to VARS, we're going to normal CDF because we have a normal distribution, and we want to know what's the cumulative density function, the area below the graph. So now we want to know what is the lower limit, what is the upper limit. You need to identify all of these. The mean and the standard deviation. Guys, again, if the question doesn't mention anything about confidentiality of the data, you are allowed to use your X values. You do not have to make any changes. You don't have to convert them into Z. Absolutely fine to use your X value. So my lower limit is 1 and my upper limit is 2. So I have 1, I have 2. lower limit, smaller number, upper limit, larger number, lower limit, upper limit. Well, what's the mean? The mean as the data, 1.5. What are the standard deviation? 0.25. Okay, calculator comes to our help. Second bars, normal CDF, lower limit is 1, upper limit is 2, mean is 1.5, standard deviation is 0.25, and paste. Well, I have 95.45%. Approximately, it is 95.45%. The probability, what's the meaning of that? It means that the probability that I randomly select a user and that user keep the phone between 1 to 2 years is 95.45%. That's the probability. So if I randomly select a person, the probability that person keeps the phone between 1 to 2 years is 95.45%. That's the meaning of that. That's the interpretation. Thank you, Abby. So as you can see, we have a survey. You're the statistician. You ran a survey. A shopper spends an average. Well, we have a keyword, everybody. Average of 45 minutes. And another keyword with the standard deviation of 12 minutes in the store. Well, the length of the time spent in the store are normally distributed. Okay, they're represented by X values, and it doesn't mention anything about confidentiality of the data or not. So we're going to assume that the data are publicly accessible. Question says, find the probability that shopper will be in the store between 24 to 54 minutes. What is the probability that they spend more than 39 minutes in store? Let's take a look at our board. So here we have the following. So this is our example. Our example says, I have the following case. We want to know what is the probability that our X is bounded between 24 minutes to 54 minutes. Again, since it doesn't mention anything about confidentiality of the just leave your X as it is and use your calculator using normal CDF for X. So remember that it's in between. It means that my lower limit and upper limit are already given to me. Lower limit, and I have my upper limit. Well, okay. So I need to use my calculator, normal CDF, second bars, normal CDF. Again, if you're using TI84, just use parentheses, your lower limit, your upper limit, and the mean, which is given to us as, let's see, the mean is 45 minutes, and the standard deviation is 12. Or if you're using TI84 and upper or your emulator, the lower limit is 24. The upper limit is 54, mean is 45 minutes, and the standard deviation is 12 minutes, okay? So let's use our calculator. The second Mars, normal CDF. Well, I have 24. Well, the next number is 54, and then we have 45, and then we have, let's see, standard deviation, which is 12. Cool, all's done. 73.33%, 73.33% approximately. So what's the meaning of that? It means that if I randomly select a shopper and that shopper spends between 24 to 54 minutes in the store, is 73.33%. Okay, the second one says, hey, now what is the probability that that random person spent more than 39 minutes in the store? More than, it means that your lower limit is given. More than, your lower limit is given. This is your lower limit. Upper limit, it must be a positive number, a large positive number. Why is that? Because the graph continues. So second was normal CDF. And then if you're using TI84, just use your lower limit, which is 39. Upper limit, use a large positive number, like 100, like 1,000, comma, mean is 45 minutes, and standard deviation is 12. If you're using TI84 for your emulator, the lower limit is 39. The upper limit is a large positive number like 100, 1,000. Mean is 45 minutes with standard deviation 12 minutes. Very good. So let's do the calculation. Second bars, normal CDF 39, 100, mean is 45, standard deviation is 12, and paste to the calculation for me. It's 69.15%. 69.15%. That's the probability that you randomly select the person and that person spends more than 39 minutes in the store. So the second part of the question says, well, how many shoppers would you expect to be in the store? How many shoppers? Okay, I have the probability. Now I want to know how many shoppers. Well, okay, there is a very simple calculation. How many people are in the store? The same as for this guy. How many people are in the store? What are we going to do? Well, this calculation is just the basic calculation. What are you going to do? Remember that the question says, suppose you have 200 shoppers enter the store, okay? What is the number of people who spend between 24 to 54 minutes in the store? We have the probability. We have that area. We just need to do the multiplication. 200 people times 73.33% or just 0.7333. The same as here. If you assume 200 people entered in the store, how many people spend more than 39 minutes? We have the probability. It is 0.6915. Very good. So if you multiply these two numbers together, you're going to get about 147 people in the store. Okay, so it means that in the store you have 147 customers who spend between 24 to 54 minutes. What about the second one? If I multiply 200 by 0.6915, how many people you have? Do the calculation and give me the number. So we get about 139 customers or people in the store who are spending more than 39 minutes. So they can use this information when they are constructing a new store. They use this information to make the capacity of the store to be as accurate as it is. Based on the data that they have, they make predictions for the new construction or the new store. That's why you see some stores are smaller than the other ones, because based on the past data, the number of people who spend time in the store might be as small as 147 or might be as large as 1,000. Very good. So remember that we said that suppose X represents a continuous random variable, and suppose you want to convert that into a confidential data type, Z value, Z score. So let X be a continuous random variable. Well, we can use Z, which is defined as X minus mu divided by sigma. Okay, we use this machine, X gets into this machine, and you get your Z as the value. So X is your input. X as the input, the machine, X minus mean, divided by sigma, and it gives you Z values, all right? Well, now I expect you to ask, what if I have Z and I want to know what was the actual data? What was the actual number that I was working with? Okay. Now, suppose X is not given. What is given? Z is given. To find your X, the X value, we use just a simple algebra. Multiply sigma and Z and add mu to both sides. So Z times sigma is equal to X minus mu. So X becomes Z sigma plus mu. So take a look at this. Now you just enter your Z value. Z is the input, and the formula that you're going to use is Z sigma plus mu. Z sigma sigma Z plus mu, and it gives your X back. So you're going to get your X back as the output. This is your input, and this is your output. Okay. So I give you two formulas, two machines that you can use to either find your Z, or if Z is given, you can find your X value. Let's take a look at a couple of examples to feel more comfortable about what's happening here. Okay, perfect. Let's ask a volunteer from group 3 to read the example for us. Very good. So in this example, you have a weight records of the weights of the cats. You do not have the actual weights. What do you have are the z-scores. So when you see 1.96, it says, hey, my z-score of the weight is 1.96. And it says, I have a negative weight. Guys, the actual weight cannot be negative. Even a dead cat has some, weight. So if you have a negative sign and it says, hey, it's a weight, it means that you're dealing with the z-score. You do not have the actual x values. Well, it says, hey, z is equal to 0. Okay, it means that your standardized z is given. It means that we're looking for our x value. Let's take a look at the board. On the board, we have the following machine. It says my x is nothing but z times sigma plus mu. It means that I enter my z into this machine and it gives me the weight or the output back, all right? So let's do the computations. Let's go to our little board here. Let's erase it. And I'll do the computation. Okay, perfect. So again, now we have our z. They go into the box. And you get your x values back. Z times sigma plus mu, and you get your x values, the actual weights back, x values. Okay. What is the first z value? The very first z value is 1.96. So what is x? X is z times sigma plus mean. But do I have information about mean? Well, it says, hey, mean weight is 9 and the standard deviation is 2 pounds. I have this information. So my x, the weight of the cat, is 1.96 times sigma, which is 2 plus. You copy down the plus sign, mean is 9. What is the weight of that cat? The second one, z is negative 0.44. I want to know what is the weight associated to this z value. I have a formula, z times sigma plus the mean. X is z negative 0.44 times sigma, which is 2, plus the mean, which is 9. What is my weight? And finally, the last cat with z equals to 0. What is the weight of that cat? X is z times sigma plus mean. So x becomes 0 times 2 plus 9. Okay. By doing the computation, the very first weight is about 13 pounds, 12.92 pounds. The actual weight of the cat. Exactly. The second one is associated to x equals to 8.12 pounds. The weight of the second cat. And finally, the weight of the last cat is just 0, so it's going to be 9 pounds. X value. So that's how we find the x values when the z is given to us. So the score for the standard test, normally distributed. the mean of that test is 50 and the standard deviation is 10, well, the applicant to be considered for higher, they need to have scores in the top 10%. Well, what is the lowest score that a person, an applicant, can earn and still be eligible to be hired by that agency? So we want to know what is the X value, right? What do we have? We have the mean, we have the standard deviation, and we want to know what is that X value. If we go back to the board, if we take a look at our board, it says, hey, if you have your Z, you can find your X value. Again, if you look at the larger board, if you have your Z, then you can find your X value. You can enter your Z to this formula, sigma times Z plus mu, and find your X value. But here we don't have the value for Z. What do we have? We have the top 10%. The question is, well, how can I use this probability 10% and find the Z associated to that 10%? So let me go to the board and explain that for you. So in many cases, we have the probability. Again, guys, when we're talking about the probability, we're talking about the area below the graph. We have the probability. We can use the probability to find the Z scores. The functionality that you're going to use is inverse norm. In our calculator, what are you going to use? You're going to go to second, you're going to go to vars, and then you're going to use the inverse norm. Inverse norm. So again, a quick recall for you. Quick recall. If you're finding the probability that X is less than A, and you have a normal distribution, you're going to go to second, you're going to go to vars, and you're going to use normal C, D, F. Then you have your lower limit, which is like -10, -100, a very small number. You're going to have your upper limit, which is A, the mean, and you have your standard deviation. If it says, hey, the probability that X is larger than B, you're going to follow the same for a normal distribution. A normal distribution. We're going to go to second, vars, normal distribution, normal CDF, and your lower limit is B. Your upper limit is a large number, like 100, 1,000, then the mean and standard deviation. In between is in between. You have your lower limit, you have your upper limit. But this case is different, guys. It says, hey, you do not have your X, you do not have your Z. what do you have? You have the probability. This number, this value is given to you. You can use the probability to find your Z. After you find your Z, then you can find your X. You can find the X value. Well, X value becomes Z times sigma plus the mean. So these are the steps that you're going to take. Move this a little bit more. See this before. X is Z times sigma plus the mean. Very good. Let's go to the board and see what do we have. So in this example, we know that it must be top 10%. Top 10%, where is that located? Let's take a look at your graph. This is my graph, top 10%. Top 10% is going to be here. 10% of 100%, but it is top 10%. Top 10%. Okay, so what is the Z value for top 10%? What is this Z? So first we need to find Z, then we're going to find our X value. Okay, let's use our calculator. To find Z, you're going to use your inverse norm. So go to second, vars, inverse norm. Okay, let's take a look at this. Just turn on the calculator, second vars, and then inverse norm. Inverse norm, well, the area is 10%. Okay, so the area is 10%, 0.10, and the mean is 0 because you are trying to find your Z. Mean is 0 with standard deviation 1. So 10%, 0.10, mean is 0, standard deviation is 1. Let's do the paste. The number that is written here is negative because it gives you the Z value on the left-hand side. The calculator computes the area to the left. So since mean is 0, the Z, which is mirror image of negative 1.28, is going to be positive 1.28. Okay, it wasn't that hard. I used second, vars, inverse norm. The calculator computes a negative Z-score, which is the mirror image on the left-hand side, negative 1.28. But since I have the top 10%, this is the below 10%, the lower 10%. This is what your calculator has inside it. It's built into your calculator, lower 10%. Here you have the top 10%. Your calculator only has the left area, lower 10%. It gives you negative 1.28. So you're going to change the sign into a positive 1.28 and use this Z to compute your X value. So you know that X is equal to sigma times Z, Z times sigma plus the mean, all right? So let's just enter all of this information and find our X. X becomes Z, which is 1.28 times sigma. Sigma is given in the question, all right? It says the standard deviation is 10 and the mean is 50. So if we do the computation, if we just multiply these two numbers and add 50 to it, you get 62.8. So this is the minimum. minimum score, that still be considered for hiring.